US Physics Olympiad year 2023 USAPHO final round. Problem A3. The motive power of ice. In the Carno cycle, a gas is heated at a constant temperature Th and cooled at constant temperature Tc. Furthermore, no other heat transfers occur and all other steps of the cycle are reversible. The laws of thermodynamics state that any such cycle must have efficiency nu equal W over Q in, where W is work done by gas and Q in is heat input inside the cycle, which is equal to 1 minus Tc over Th. Below we will explore two other heat engines which recover this efficiency in certain limits. Part A. Consider the following heat engine involving 1 mole of ideal monatomic gas. The gas begins at temperature T0, pressure P0 and volume V0 and undergoes 4 reversible steps. First step. The gas is expanded at constant pressure until its temperature rises to 1 plus beta multiplied by T0. Second step. The gas is expanded at constant temperature until its pressure falls to P0 over alpha. Step 3. The gas is contracted at constant pressure until its temperature falls back to T0. Step number 4. The gas is contracted at constant temperature until its pressure rises back to P0. First question. Which steps require heat to be transferred to the gas? For each such step, give the total heat input in terms of P0, V0, alpha and beta. Second question. Under what conditions on alpha and beta would we expect the efficiency of this heat engine to approach that of a Carnot cycle, working between the same maximum and minimum temperatures? Third question. Find the efficiency of this heat engine for general alpha and beta. Solution for Part A. First question. Which steps require heat to be transferred to the gas? For each such step, give the total heat input in terms of P0, V0, alpha and beta. Solution. Obviously that heat is added to the gas in the first two steps, from this point to this point and from this point to this point. In the first step we have heating at constant pressure, which has a molar heat capacity Cp equal 5R over 2. So from here we have Q1 equal Cp multiplied by delta T, and delta T is beta T0. Using universal gas law we have RT0 equal P0 V0, and we have finally that Q1 equal 5 over 2 beta P0 V0. In the second step, the heat added to the gas compensates for the work done while it expands. So we have Q2 equal 1 plus beta RT0 logarithm V final over V initial. Again, RT0 equal P0 V0, and the relation V final over V initial is back proportional to a relation for pressures for constant temperature. It means that this relation is just alpha. And finally we have Q2 equal 1 plus beta multiplied by P0 V0 logarithm alpha. With the same reasoning we can count what is Q3 and Q4. Q3 will be the same as Q1 but negative. because that's equal to Cp multiplied by delta T, and delta T is negative delta T from the first process. So it means that for Q3 we have negative 5/2 beta P0 V0. And finally Q4 equal work done over gas with the constant temperature, which is again RT0 logarithm Vf over V initial, but now they are reversed. So it means that sign is negative here. Finally, we can count what is total work done by gas. That will be this expression, or beta P0 V0 logarithm alpha. And now we can count what is efficiency for this process. That will be work done by gas over Q in. And the Q in is just Q1 plus Q2. And finally we have this expression, which is answer for question 3. But now let's compare it to efficiency for Carnot cycle. For Carnot cycle with the same high and low temperatures, we have beta over 1 plus beta. Let's compare it with the formula for our process. Here, if beta is infinitesimal, this efficiency will be almost the same as for Carnot cycle. So it means that only for beta much less than logarithm alpha, we have efficiency going to efficiency for Carnot cycle. But this happens only when beta is very small. It means that delta T is very small and going to 0. This is the only condition for which this efficiency could be compared with the efficiency for Carnot cycle. So totally this is the full solution for part A. Part B. Now consider a heat engine built around the freezing and melting of water, which occurs at a pressure-dependent temperature Tc from P. Initially, a volume of V of water is squeezed underneath a piston so that it experiences the total pressure P1, and the water is on the edge of freezing with the temperature Tc from P1. The engine then undergoes 4 reversible steps. First step, a mass is slowly placed on the piston, raising the total pressure to P2. Second step, the water is cooled to temperature Tc from P2 and frozen. Step 3, the mass is slowly removed from the piston, lowering the pressure back to P1. Step 4, the ice is heated back to temperature Tc from P1 and melted. Assume that water and ice are incompressible with the fixed densities ρ W and ρ C. First question. What is the net work done by this engine in terms of P1, P2, V and the densities? Second question. Assume the latent heat per unit mass L to melt ice is large, so that freezing and melting account for essentially all of the heat transfer in the cycle. What is the efficiency of the engine in terms of P1, P2, L and the densities? Third question. Since we assumed all heat transfer occurs during melting or freezing, this cycle has the same efficiency as the Carnot cycle in the limit where P1 and P2 are very close. Use this fact to enter an expression for delta Tc over delta P in terms of Tc, L and the densities. Solution for part B. Question 1. What is the net work done by this engine in terms of P1, P2, V and the densities? Solution. The system expands at the pressure P2 and contracts at a pressure P1. So the net work done is pressure difference, which is P2 minus P1, multiplied by delta V. So that's process 2 and 4. So using expression for delta V through V, rho W and rho I, we can get this expression for work. That was solution for the first question from part B. Question 2. Assume the latent heat per unit mass L to melt ice is large, so that freezing and melting account for essentially all of the heat transfer in the cycle. What is the efficiency of the engine in terms of P1, P2, L and the densities? Solution. We know that efficiency equal work done during this process, which we counted in the first question, divided by Q in. The heat transferred in is used to melt the ice. So we have Q in equal rho water multiplied by volume V and multiplied by latent heat L. And the work done by process was counted before. That was this one. So finally efficiency equal to this expression, which is a solution for question 2, part B. Question 3 from part B. Since we assumed all heat transfer occurs during melting or freezing, this cycle has the same efficiency as a Carnot cycle. In the limit where P1 and the P2 are very close, use this fact to infer an expression for delta T over delta P in terms of Tc, L and the densities. Solution. The Carnot efficiency for the same high and low temperature is this one. T high minus T low divided by T high. Efficiency for Carnot cycle equal to this expression, where TCP1 is high temperature and TCP2 is low temperature. For our process we have efficiency which we counted in question 2. Now equalizing this, we have these equalities. Now combining, we can write this expression, and for P1 going to P2 we have as a limit first derivative from temperature by pressure equal this expression. This was solution for question 3 part B, and here we finished discussion for problem A3.